What if the next drone following you isn't being controlled by a human at all? That question is no longer science fiction. In Project Pilot, Anthropic and Andon Labs tested whether today's frontier AI models can autonomously control an off-the-shelf drone to find, identify, navigate toward, and follow a person. In this video, we'll break down DroneBench, the 5 challenges an AI must master. From reconstructing its environment and navigating around obstacles to detecting and tracking a human. We'll look at what the latest models can already do, where they still fail, and why this experiment raises some serious questions about AI, privacy, surveillance, and human oversight. So, how close are we to truly autonomous AI-controlled drones? Let's find out.
Hey everyone, welcome to this explainer. For a really long time, the artificial intelligence we've been interacting with has been, well, safely trapped behind a digital screen. You know how it goes. We type in a prompt, it spits out some text or a cool image, and that's pretty much the end of the transaction. But what happens when frontier AI models are actually given physical agency? Like, what happens when they are handed the controls to commercial hardware out in the real world? Today, we're diving into Anthropic's newly declassified research, Project Pilot. We're going to look at the fascinating and honestly slightly terrifying reality of AI taking flight.
So here is the core high-stakes question. Can an AI agent autonomously hunt and track a human using an aerial drone? Anthropic, along with their partners at Andon Labs, set out to answer exactly that. And they didn't just run some clean, perfect computer simulation. No way. They wanted to see if modern AI could actually navigate the chaotic, messy physical reality of a standard office space to find a specific person.
All right, Section 1. AI enters the physical world. To really understand how we got here, we have to look at Anthropic's fundamental shift toward giving frontier models physical agency and how they test their ability to operate real-world machines. What's truly staggering here is the sheer speed of this evolution. We're talking about all of this happening over just the past year. First, we had Project Vend, where AI models were tasked with running a small physical shop. Then came Project Fetch, which gave us an early look at using AI to operate a robot dog just to retrieve a beach ball. And now we have Project Pilot, where AI is literally tasked with flying an aerial drone. The jump from static operations to grounded robotics to full three-dimensional aerial movement is incredibly rapid. Moving on to Section 2, the Drone Bench Challenge. Now, you might be picturing some million-dollar military prototype for this, right? Actually, researchers tested these AI models using a commercially available DJI Tello EDU drone. It's an off-the-shelf drone that retails for just $129, and they flew it in a standard, everyday office environment. Now, we have to acknowledge that this technology is fundamentally dual use. On one hand, automated person detection and tracking have massive legitimate utilities. Think search and rescue missions, disaster response, lawful public safety, stuff that saves lives. But on the flip side, these exact same capabilities present severe risks of abuse. We're talking about everything from the overreach of legitimate authority to totally unaccountable private surveillance. Anthropic's Frontier Red Team ran this experiment specifically to measure that exact tension between the benefits and the risks. Which brings us to the exact definition of DroneBench. It is a rigorous benchmark designed to test if AI models can use a drone to autonomously perform an indoor locate and follow surveillance task. To create a baseline for success, they actually brought in human AI coding teams to craft algorithms for this exact mission. The goal wasn't just to see if the AI could fly, it was to see if a fully autonomous AI could match or even beat a team of human experts who were equipped with AI tools. Section 3. 5 Steps to Flight. Telling a drone to find that person sounds like a simple command to us, but for an AI, the researchers had to break that massive command down into distinct, measurable actions. So it's kind of like a giant puzzle with 5 complex subtasks the AI has to execute in real time. First is reconstruct. It has to turn flat video feeds into a 3D model and slice that into a 2D obstacle map. Second, localize. It has to figure out where the drone actually is on that map. Third, navigate, planning a flight path between rooms without crashing. Fourth is detect. Once it's in the room, it has to find the target human using a reference photo. And finally, follow. It must control the drone to keep that human centered in its view, even as they move around. And remember, all of this has to happen continuously. Okay, you have to hear this because it's absolutely brilliant. The AI models came up with incredibly creative ways to solve these problems. During one run, a model needed to figure out the exact tilt of the drone's onboard camera. Instead of just failing, the model analyzed the video feed, noticed the grout lines on the office floor, and used them to extrapolate a vanishing point. It successfully calculated the camera tilt to within 4 degrees of the true value. It literally grounded itself in the physical physics of the room before it even took off. Section 4. Grading the frontier models. Anon Labs put 15 different models to the test, but we are going to put the spotlight on the absolute top performer of the whole group, Claude Fable 5. Looking at its report card, the difference between where the AI excels and where it stumbles is incredibly stark. There is a massive spike in success rates for the detect and follow tasks. The model is so smart at identifying targets from a photo and tracking them dynamically. However, it struggles immensely with reconstruct and localize. The AI just has a really hard time with spatial mapping and understanding exactly where it is located within a 3D environment. But when it gets the tracking right, it is astonishingly good. In the final tracking stages of the mission, Claude Fable 5 actually followed the reference human more closely and accurately than the baseline algorithm created by the human experts. It locked on and straight up outperformed the human-guided code. But here is the plot twist. Because the model is so weak at step 1, reconstructing that physical space, its successes in tracking can be entirely undone by a physical world blind spot. In one end-to-end physical test, because of compounding spatial errors, Fable 5 confidently flew the drone right into what it thought was a doorway. Actually, it was a solid wall. It caused a complete catastrophic crash. Which brings us to Section 5, the consistency gap. That wall crash highlights a massive difference between an AI achieving a complex physical task once and an AI being trusted to do it reliably every single time. The researchers actually quantified this gap, and the magic number is 6 months. Currently, the frontier of peak AI capability is running about 6 months ahead of its consistent average reliability. To put that into perspective, Fable 5's average consistent performance today is roughly where previous models' absolute one-off best performance stood 6 months ago. So, the AI can do it just can't do it reliably on command. Yet. Now, to maintain some objective clarity here, we need to temper expectations and look at the limitations of this initial pilot. The drones they used were moving at very slow speeds. The test was conducted in a single, controlled office floor plan. There were a limited number of people around to avoid confusion, and everything was strictly indoors. So for sure, this is not yet a robust, all-weather outdoor surveillance system. However, we really shouldn't be lulled into a false sense of security by those current limitations. The report explicitly states that once the spatial reconstruction error is fixed, which, let's be honest, is just a matter of time and processing power, full end-to-end performance will suddenly be within reach. Full AI autonomy won't be some magical, discontinuous jump out of nowhere. It is literally just waiting on one final puzzle piece to snap into place. Section 6. The human in the loop. As these AI models rapidly approach reliable physical independence, the entire era of keeping a human in the loop is being totally challenged. Let's draw a parallel here. Think back to the early days of AI software agents. Humans approved almost every single tool call-out out of an abundance of caution, right? But look at current software agents today. We just trust them to execute long-horizon, complex tasks with minimal intervention. Physical robotics, as proven by DroneBench, are rapidly approaching this exact same threshold. The leap from supervised digital assistant to autonomous physical agent isn't science fiction. It's happening right now. Which leaves us with this final, provocative thought to conclude our explainer. Right now, keeping a human in the loop is an easy decision, because it prevents costly mistakes while the AI is still learning. But when AI robotics pass that reliability threshold, when they stop crashing into walls and start executing perfectly every time, will human oversight still be treated as a crucial safeguard for physical security and privacy? Or will companies and governments start viewing the human in the loop as just an unnecessary financial cost? Technology developers and society at large are going to have to figure out these governance frameworks, and soon. Thanks for joining me for this explainer, and keep your eyes on the skies.